Alright, thanks for watching and welcome to the 9th way of doing the Gaussian integral. I know, this just gets crazier and crazier. And today we will do it the Stirling way. So what do I mean by that? So it turns out there's a formula called Stirling's formula. And it's actually a very nice formula. It tells you how n factorial grows. So it turns out n factorial, at least if n is very large, grows like n to the n over e to the n square root of 2 pi n. And as n goes to infinity, all this means is the ratio of the two goes to 1. And speaking of Stirling, if you're ever in Las Vegas, there's a Stirling brunch. That's excellent. You should try it out. Okay, and what I'm gonna do today, it's a little bit cheating. I'm not gonna prove the formula for the Gaussian integral, but I want to show that this square root of 2 pi actually comes from the Gaussian integral. So the square root of 2 pi is precisely the value of the Gaussian integral, more or less. Okay. All right, and turns out for this one, you have to use a result from a previous video I made with the Wallace formula. So just recall the following. So that was, I think, video 7. We define our powers of cosine. So In was the integral from 0 to pi over 2, cosine to the n of theta d theta. And we proved a nice sort of recursive formula for those INs. So we proved that I of 2n equals to 2n minus 1 over 2n I of 2n minus 2. I think I used some sort of integration by part for that. And it's nice, it tells you how, at least for even n, how I to n relates to like 2 steps before. Okay, and now somehow we can use this formula, again not quite clear how, to prove our Stirling's formula. So, step 1. So I of 2n, well, that's 2n minus 1 over 2n, I of 2n minus 2. But of course, because it's recursive, we can just continue that way until we arrive at I0. So this becomes 2n minus 1 over 2n. Now, the next term, notice this is really 2 times n minus 1. So we can do the same thing, but with n minus 1 instead of n. So the next term will be 2n minus 3 over 2n minus 2, I of 2n minus 4. So 2 steps beforehand. And notice all that really is, it's on the top, we just have odd numbers. Go to form 2n plus 1, right? And on the bottom, we have even numbers. 2n times 2n minus 2, etc., etc. So at the end, you should expect that at the top, you just have the products of odd numbers, and at the bottom, you have products of even numbers. And indeed, that is true. Ready? Second. Maybe it's this side. Hello. My God. Oh, okay. It was the other side. Okay. So, welcome back. What we have then is that indeed this product equals to 2n minus 1 times 2n minus 3 dot 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 times 5 times 3 times 1 over 2n minus 2 dot 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 times 6 times 4 times 2. again, the product of all the odd numbers starting at 2n minus 1 and the product of all the even numbers starting at 2n in decreasing order. And in the end, the last term becomes I of 0. And remember, I of 0 is the integral from 0 to pi over 2 of cosine 0 theta d theta. But that's just 1. So the integral is just pi over 2. All right, now, let me see. Yeah. Ideally, we would like to write the numerator as a factorial. It would be nice to have 2n minus 1 factorial, because then we can use Stirling's formula, more or less. Well, in order to turn it into a factorial, we just have to fill in the missing pieces. So 2n minus 2, 2n minus 4, and then maybe here's a 6, here's a 4, here's a 2. And notice what's cool is that all the missing pieces reappear on the denominator, except for this 2n. So, in the end, what this becomes, it's 1 over 2n, right, that missing piece, and then 2n minus 1 factorial over, on the one hand, the product of all those things, because they're still here, they didn't leave, 6, 4, 2. But because we need to complete the numerator, we need another series of 2n minus 2 up to 2. That's why it's this times this again, but it's just that square, and then I naught is pi over 2. Okay, and it turns out the denominator, you can also write it as a factorial. That's what makes it so nice. So 1 over 2n, 2n minus 1 factorial. And then let's see, let's collect the 2's. So 2 times n times 2 times n minus 1 dot 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 times 2 times 3 times 2 times 2 times 2 times 1 squared times pi over 2. And what do we have? Notice we do have n minus 1, and then 3 times 2 times 1. So, sorry, there's no more 2n. Sorry. I was like, there's a factor missing here. Anyway, so we get 2 times n minus 1 times 2 times 3 times 2 times 2 times 2 times 1. And then at the end, here we get n minus 1 factorial. And then how many powers of 2? Well, just n minus 1. So we get 1 over 2n over 2n minus 1 factorial over, well, 2n minus 1 squared and n minus 1 factorial squared. Squared times pi over 2. All right, that's very good. So what have we calculated? We've shown that I of 2n equals to 1 over 2n times bunch of factorials. 2n minus 1 and, n minus 1 factorial. So let me write that down. So we have I of 2n equals to, so 2n minus 1 factorial over 2n, 2n minus 1 times n minus 1 factorial squared times pi over 2. And now we would like to use an analog of Stirling's formula, but without that constant square root of 2 pi, in order to derive our constant square root of 2 pi. And it turns out there is such a formula. It's called de Moivre's formula. And I love that name because de Moivre sounds like de poivre. And poivre means pepper in French. So pepper. And Speaking of which, if you're in Irvine, there's this wonderful place called Pepper Lunch, which is also good. So, there is de Moivre's formula, which just says that asymptotically, n factorial, it's like c to the n over e to the n square root of n as n goes to a factorial, n goes to infinity. And notice that's precisely Stirling's formula, except without the constant. And really our goal is to show that c is square root of 2 pi. Using, you'll see, the Gaussian integral. And lastly, de Moivre, you may have seen it before. It's also, I think, it's the one who came up with this formula for e to the I n theta. So basically e to the ix to the n equals to e to the nix, which basically tells you that cosine of x plus I sine of x to the n is cosine of nx plus I sine of nx. So de Moivre came with this very nice formula. Impressive. Okay, but this is not why we're here today. We're here for this expression. All right, now that we know that I of 2n has those bunch of factorials in it, and we have this nice expansion for n factorial, let's just plug this into this formula. So what does that tell us? It tells us that I 2n asymptotically equals to that constant times. Instead of n, it's 2n minus 1. So 2n minus 1 over e to the 2n minus 1 square root of 2n minus 1 over 2n times 2 to the n minus 1 and the same spiel but with n minus 1. So c times n minus 1 over e to the n minus 1 and square root of n minus 1 squared. And don't forget about the pi over 2. Now, we would like to clean this up a little bit. So this equals to, let's see, c times 2n minus 1 to the 2n minus 1 square root of 2n minus 1 and then 1 over e to the 2n minus 1. Now, let's expand out that square. So 2n times, so 2 to the 2n minus 2 c squared n minus 1 to the 2n minus 2 and then 1 over e 2n minus 2 and then times, I think, n minus 1. Let me see. Well, we're squaring the n square root of n minus 1, so n minus 1. And don't forget about the factor of pi over 2. And let's see what we can cancel out. Turns out there's a bunch of stuff we can cancel out. Like this squared cancels out. And then also this 1 over e cancels out. Because we have 2n minus 1 over 2n minus 2, which means there's just this extra factor of e, I believe, on the denominator. Because it would be 1 over e to the minus 1, but then it just becomes e. And also, you know, this n minus 1, I think you can put it here, but we're not going to deal with that right now. And then what's the next step? Well, let me see, there's a yeah. We'll see what the next step is. So the next step then is to write just group terms that are alike. So it turns out then what you get. Now I regret using the backboard, but we get I to the 2n is equivalent to, so we have this 1 over c And then we have the 1 over 2n. We still have this 1 over 2n minus 2. So 2 to the 2n minus 2. And then, so this 2n minus 1, yeah, you can take off the minus 1 here. So it becomes 2n minus 1 to the 2n. And then you can just write the square root of 2n minus 1 as square root of 2n minus 1 over 2n minus 1. So that takes care of the numerator. And then, what about the denominator? Well, there's just this factor of n minus 1 here. So n minus 1 to the 2n minus 2 times n minus 1, which you can just write as 1 over n minus 1 to the 2n, and then n minus 1, and then n minus 1 squared. And there is a reason I'm writing it in such a weird way. And then lastly, there's this 1 over e, and there's pi over 2. I know, you're like, what the hell is going on? Trust me. Trust me, I know what I'm doing. So what we get then is 1 over c, 1 over 2n, 1 over 2 to the 2n minus 2, and then, so 2n minus 1 to the 2n, and then 2n, and then this becomes, so this simplifies to square root of 2n minus 1, and then 1 over n minus 1 to the 2n, and then 1 over n minus 1, and then 1 over e, and then pi over 2. Here's why it's useful. It's because of those two terms. So notice, other than this 2 to the 2n minus 2, those are the only terms which have powers of n. And the reason this is nice is because now we have the following formula, and which makes sense if you think about it. Namely, what do we have? Because let me tell you what I'm trying to do. I'm trying to write this in terms of exponential functions, because it turns out then they simplify quite nicely. And by the way, it's still not clear how we use the fact that in is the power of cosine, but this will be clear at the end. Now, notice, so remark. Remember the following limit from calculus. So 1 plus a to the n, turns out as n goes to infinity, it goes to e to the a. EA Sports, to the game. I promise you I was not sponsored by all those things, it's just fun. Okay, then, what's nice about this, you can put this on a common denominator, so we get n plus a to the n over n to the n goes to e to the a. And in particular, so cross-multiplying, what this tells you is that asymptotically, n plus a to the n is roughly asymptotic to n to the n e to the a. Which is sort of a nice binomial expansion of n plus a to the n. And now let's see what happens in this case. So here, the nice thing is, and again, this is a squiggle, this is not an n. The nice thing is, this is like n plus a to the n, except n here is 2n, a is minus 1, and same thing here, I think, yeah. This is n minus 1 to the n squared. So n is n and a is minus 1. So what happens then is I of 2n is then equivalent to, again, all our terms, 1 over c, 1 over 2n, 1 over 2 to the 2n minus 2. And now, using this identity, so using this with this, we then get that this is asymptotic to, let's see, 2n to the 2n, e to the minus 1. Okay, so that's good. And we still have this 1 over square root of 2n minus 1. So maybe here, 1 over square root of 2n minus 1. So here, if a is minus 1 and 2n. Okay. And continuing with this term, we indeed get, so notice again, this is 1 over n minus 1 to the n squared. And then we get, so 1 over n to the n squared, and then e to the minus 1 squared. And we still have this 1 over n minus 1, this 1 over e, and this pi over 2. Minus 1 over e, and pi over 2. And it turns out, using this, there's a nice cancellation. So let's, if you like, write this out. So this becomes, okay, I promise you, almost done. 1 over c, 1 over 2n, 1 over 2 to the 2n. And then 2 to the minus 2, which is 1/4. So this becomes 4. And then, here's why it's so nice. This becomes 2 to the 2n times n to the 2n. And then we still have 1 over e, 1 over square root of 2n minus 1, and then 1 over n to the 2n, e to the minus 2 over 1, so that's e squared, and then 1 over n minus 1, 1 over e, and then pi over 2. This is not for weak people, okay? This is intense math, but here's why it's nice. This term cancels out, and then also this term cancels out. So the terms we were worried about cancel out, and then you're just left with those nicer terms. And also, not only that, this 1 over e cancels out with this e squared, and, well, 4 and 2, they cancel out to become 2. Okay, and then let's see, what are we left with? We then are left with sort of terms that are not that bad. Wait, I realize there's another typo, but don't worry about it. So then we get I to n is asymptotic to 1 over c, 2 over n, and then 1 over square root of 2n minus 1. Okay, and let me just see, so, yeah. So I realized here I made a typo. I wrote n minus 1 over n minus 1 squared. It was supposed to be on the denominator, so it sort of comes to the numerator. So sorry about that, but this becomes n minus 1. And then also n minus 1. And we get that this becomes just n minus 1 on the numerator. And still the pi over 2, which I realize you can also cancel out. Okay, and let me see, is that what we still want? Yeah, then, again, we're doing stuff asymptotically, so we just care about what happens as n goes to infinity, and then notice what we do have is that we have this term of n minus 1 over n, but asymptotically that goes to 1, and also this square root of 2n minus 1, asymptotically this 1 becomes negligible, and we get square root of 2n. So in the end, what we are left with after all this monstrous calculation is just pi over c over 1 over square root of 2n. So I to n is asymptotically equal to pi over c times 1 over square root of 2n. And remember what we want to find? We want to find this constant c. And for this now, so surprisingly, I think it was still part 2. Now we want to do part 3. This is now where we use our results from video 7 about, the Wallace way. And here is where we use the fact that I to n equals to cosine to 2n, the integral. Because now, recall, video 7. We've shown the following two things. First of all, in is equivalent to the previous term. So asymptotically, they go to the same thing, which makes sense. They do converge. And, or maybe not, we'll see. And we also had this other nice estimate that says the following. And in fact, let me do it on a new whiteboard. Perfect, there we go. So in video 7, we've shown the following identity. Namely, the integral from 0 to square root of n, e of minus y squared dy, it's squeezed between square root of n, I, 2n minus 2, and square root of n, I, 2n plus 1. Okay. So we have shown this in video 7, and moreover, in video 7, we've shown that in is just asymptotic to in minus 1, and therefore, in particular, the in's are all sort of asymptotic, so this is really asymptotic to square root of n, I to n, and this then becomes asymptotic to this, and this is also, no, let me do it better. So, this term is asymptotic to square root of n, I to n. Because again, no consecutive terms are asymptotic, and this term is also asymptotic to square root of n, I to n. Which means, sort of by the squeeze theorem, this term is also asymptotic to square root of n, I to n. All right. And here is now where we use the identity that we derived here. Well, I of 2n is asymptotic to pi over c, 1 over square root of 2n. So this thing is also asymptotic to square root of n, 1 over, so pi over c, 1 over square root of 2n. And the nice thing is, the things we were worried about, this square root of n and this square root of n here, they cancel out, and we get pi over c square root of 2. So as n goes to infinity, this becomes sort of equal to this, and because this is constant, we can let n go to infinity. So now let's do that. Let n go to infinity, and we get integral from 0 to infinity, e of minus y squared dy equals to pi over c square root of 2. And notice what is this? It's just half of the Gaussian integral. So we just get that c, let's see, what do we get? We know that this is square root of pi. And again, remember our goal was to show what c is using the fact that the Gaussian integral here is square root of pi. So square root of pi is pi over c square root of 2. And then cross multiply c square root of 2 square root of pi equals to pi. And then c is just square root of pi over square root of 2. No. Let me see. Sorry. So this is not square root of pi, it's half of the Gaussian integral. So square root of pi over 2 equals to pi over c square root of 2. And then just cross multiply, so c square root of 2 square root of pi equals to pi, 2 pi. And therefore, we just get that indeed c is square root of 2 pi. Which is what we want. Why does that solve our problem? Because remember, we had the de Moivre's formula, which just says that n factorial is asymptotically equal to c n over e to the n square root of n as n goes to infinity. And we've just shown that c is square root of 2 pi, so we get n factorial, it's square root of 2 pi times this, and therefore n over e to the n square root of 2 pi n. Man, should have used 2 pi m. At least I would be there. And this is precisely Stirling's formula. So using the de Moivre formula and the Gaussian integral, we get Stirling's formula, and that's exactly what I wanted to show. I wanted to show that this constant here relates to the Gaussian integral. All right, so if you like that, and you want to see more math and more Gaussian integrals, please make sure to subscribe to my channel. Thank you very much.